My name is Evan Olson, and I'll be solving problem 37 from Chapter 13 of the Fundamentals of Heat and Mass Transfer 8th edition. The problem statement says to consider the cavities formed by a cone, cylinder, and sphere which have the same opening size d and major dimension L as shown in the diagram. Part A says we need to find the view factor between the inner surface of each cavity, which is this gray surface, and the opening of the cavity, which is this orange surface. I labeled the opening of the cavity as surface 1 and the cavity itself as surface 2. Starting off with the cone, we can notice that our view factor from surface 1 to itself is going to be 0 because it is a planar surface. It can't see itself. And that makes the view factor from 1 to 2, 1 through the enclosure law. And then we can find our view factor from 2 to 1 using our reciprocity rule, which shows that the ratio of the areas between our two surfaces times the inverse view factor. So in this case, we want to find F21. So that's equal to our area 1 divided by area 2 times our view factor from 1 to 2. And since our view factor from 1 to 2 we found was 1 from the enclosure law, um, our view factor from 2 to 1 will just be the ratio of the areas. And the areas for this cone are going to be A1, which is this top surface, equal to pi over 4d squared, just the area of a circle. And A2 is the surface area of the outside of this cone, excluding the base. And that's in terms of d and L, which was stated in this problem, the area is going to be pi over 2d times the square root of L squared plus 1/4 d squared. Plugging that into our relationship, we find that the pi and 1d cancel, and we get a final view factor of d over 2, L squared plus 1/4 d squared to the 1/2. Secondly, for our cylinder, we can notice that it has the same cross-sectional area on top. So A1 is going to be equal to pi over 4d squared, and A2 is going to be equal to the area of the side of the cone, or the side of the cylinder, plus this base area, which we can lump together since we don't care about the view factor between, let's say this is surface 3, right? We don't care about that view factor from 3 to 2. We can just lump those together. So that's just going to be pi dl plus pi over 4d squared. And we can simplify that a little bit by factoring out the pi d to get pi d times L plus 1/4 d. And this has the same exact relationship for the view factor, since the view factor from surface 1 to itself is going to be 0 since it's a plane, and the view factor from 1 to 2 is therefore 1 through the enclosure law. And then the view factor from 2 to 1 follows the reciprocity rule, where we find that it is just equal to the ratio of the surface areas. So similarly here, we find that the view factor from 2 to 1 is going to be equal to 1/4 d times L plus 1/4 d to the minus 1. And finally, for our spherical geometry, this is a little bit more complicated. We know that the surface area of the opening is going to be just another circle, so that's pi over 4d squared. But now we need to find the surface area of this partial sphere with a spherical cap cut out of it. And we can delve into that relationship here. So I found online that the surface area of a partial cap, spherical cap, is equal to pi dh, where h is the total height of the cap. By taking a cross section of this, we can notice that we can make a right triangle here, and we can find that that d over 2 um, squared minus h, sorry, d over 2 minus h squared. So that is going to be this leg, plus d over 2 squared, which is this leg, equals big D over 2 squared. And then we can back h out of that, it's going to turn into a quadratic equation where we can solve for h. And since the little diameter is always going to be less than the bigger diameter, this produces both a large and a small solution, which describes either this large length here or this small length on top. And this is what we're interested in. So we are going to neglect the plus sign in this equation, and this just turns into h equals d over 2 minus square root d squared minus little d squared over 2. And then that turns into a final cap area in terms of little d and big D of pi over 2d times uh, quantity d minus square root d squared minus little d squared. And the area of the area of our partial sphere is going to be the total surface area of a sphere minus that cap surface area. And so that turns into this relationship. And the view factors of this one is the exact same as the past two. So our view factor from surface 2 to 1 is going to turn into the ratio of area 1 over area 2, which gets us a final view factor of d squared over 4l squared minus 2d, quantity L minus square root L squared minus D squared, where this L is the same exact as D. The second part says that we need to find the effective emissivity of each cavity, uh, E subscript E as defined in problem 13.33, assuming the inner walls are diffuse and gray with an emissivity of EW. So 13.33 describes that the effective emissivity is the ratio of radiant power leaving the cavity to a black body which has the same area of a cavity opening and temperature of the inner surface with the temperature of the inner surfaces. And so we can kind of draw a schematic from this. It's basically saying that we want to find the relationship between Q1 and Q2. And of course, Q1 is equal to our view factor from 2 to 1 times Q2. And so we can expand that out and find that our effective emissivity times our black body radiation is equal to our view factor from 2 to 1 times our wall emissivity times the Stefan-Boltzmann constant times temperature to the fourth. And then these two end up canceling each other, which gives us that the effective emissivity is equal to our wall emissivity times our view factor that we found in the previous step. And then the effective emissivities for the cone, cylinder, and sphere are simply just going to be the view factor that we solved in the previous problem times a wall emissivity term. And then the last part asks us to for each cavity and wall emissivities of 0.5, 0.7, 0.9 to plot the effective emissivity as a function of the major dimension to opening size ratio L over D over a range from 1 to 10. And so that just wants us to vary the ratio between D and L for each different case and see what our effective emissivity is going to be based on these equations that we derived in part B. And so MATLAB outputs this very nice curve where this blue line is going to be 0.5 Wally's emissivity, 0.7 is the orange line, and 0.9 is the yellow line. On the y-axis, we have the effective emissivity, and on the x-axis, we have our L over D ratio. And you can see for the cone-shaped cavity, as L over D approaches 10 or beyond, the emissivity approaches 0. Very similarly for the cylindrical cavity, except it has an overall lower emissivity, 0.18 instead of 0.4. And for the spherical cavity, it has a much steeper drop-off, which is interesting to see. And it looks like it approaches 0 much more rapidly.